function defined on this closed interval 0 to pi by 4 by fx equal to cos x if x is rational and equal to sin x if x is irrational. We need to show that f is not Riemann integrable. Now when the function is Riemann integrable, first condition if fx is bounded. And second condition, the lower Riemann integral should be equal to the upper Riemann integral. Yes, then we say that the function is Riemann integrable. But here we need to show that the function is not Riemann integrable. That means we need to show that these two are not equal. And first, the function is bounded. Yes, it is bounded. So this is the function given when x is lying between 0 to pi by 4, the closed interval. So in fx, two functions are given, sin x if x is irrational and cos x if x is rational. For this interval, if I take sine all over, I get sine of x here and sine 0 and sine of pi by 4 is 1 by root 2. And sine remains the same because we know that sine x is an increasing function from 0 to pi by 4, right? Whereas if we take cos all over, cos of 0 is 1, then cos of x, then cos of pi by 4 is 1 by root 2. So cos x is a decreasing function from 0 to pi by 4. So therefore the sign changes. Is it okay, fine? Yes, we can also write this cos x as greater than equal to 1 by root 2 and less than equal to 1. So from these two we can say that our function is lying between 0 to 1 for all x belonging to the closed interval 0 to pi by 4. And because this function is lying between 0 and 1, so this is a bounded function, right? Now we need to find the lower Riemann integral and upper Riemann integral. For that, we also need to find the lower sum and upper sums, right? So let's divide this interval into n equal parts to get the greatest lower bounds and the upper lower bounds. Therefore, the length of each subinterval is equal to this b minus a divided by n. So that is pi by 4 minus 0 divided by n, that is pi by 4n. So writing the subintervals, so these are 0 to pi by 4n, and then pi by 4n to 2 pi by 4n, then 2 pi by 4n to 3 pi by 4n, I minus 1 pi by 4n to I pi by 4n, and then continuing like this. At last we will be having n minus 1 pi by 4n and n pi by 4n, that is pi by 4. So this is your x0, this is your x1, likewise this is your xi minus 1 and this is xi, and this is xn minus 1 and this is xn. Next we need to find the greatest lower bounds and the least upper bounds. So this mi is the minimum value of fx in closed interval xi minus 1 xi, and this is the maximum value of fx in closed interval xi minus 1 xi. Because in this closed interval there are infinitely many irrationals and rationals, so our function can attain either sin x or cos x in this closed interval xi minus 1 xi, right? Because for rationals the function is cos x, for irrationals the function is sin x. So this function can either attain one of these two values. So let's write this first. Sin of x is less than equal to cos of x for all x belonging to the given interval 0 to pi by 4. So therefore we are taking the greatest lower bound of fx in closed interval xi minus 1 xi. I take mi to be equal to, yes, sine of xi minus 1 for x lying between this xi minus 1 and xi, and sine x is an increasing function, right? So therefore we take our mi to be sine of xi minus 1. What is the value of sine of xi minus 1? It is I minus 1 pi by 4n. Similarly, we can find this capital Mi to be, to find this capital Mi, so we take this capital Mi to be equal to cos of, xi or xi minus 1. Let's check this. Because x lies between xi and xi minus 1, and if I take cos all over I get, and because cosine is a decreasing function, so the sign changes, and therefore we need to take our capital Mi, that is the least upper bound, to be cosine of xi minus 1. So this is equal to cosine of, again, xi minus 1 is I minus 1 pi divided by 4n. So we have also calculated this capital Mi. And now finding the lower sum and the upper sum. It is the summation from I going from 1 to n on small mi into xi minus 1. So that is equal to the summation I going from 1 to n. What is small mi? It is this. That is sine of I minus 1 into pi divided by 4n. And xi is I pi by 4n minus xi minus 1 is I minus 1 pi divided by 4n. So when we solve this, we are getting pi divided by 4n. And taking the summation on this, we get taking pi by 4n outside. And we are getting this to be, it is sine of 0 plus sine of pi divided by 4n plus sine of 2 pi divided by 4n plus so on, sine of n minus 1 pi divided by 4n. And there is a formula for this series. If I take this to be alpha and this to be alpha plus beta, so alpha is pi by 4n and beta is again pi by 4n. The formula is sine of alpha plus n beta divided by 2 into sine of n beta divided by 2 divided by sine of beta divided by 2. Please remember this formula, and I'm going to use this formula in this series. So when applying this formula, we get sine of alpha is pi by 4n plus the number of terms are n minus 1, right? So this is n minus 1. Beta is pi by 4n and multiplied with this 2 because of this denominator. And then this is sine of n minus 1. Again, beta is pi by 4n and there is 2 over here, so I'm writing 8n divided by sine of beta by 2, that is pi divided by 8n, and also there is pi by 4n. Now from the terms in this bracket, if I take pi by 4n common, now from the terms in this bracket, if I take pi by 4n common, I will be getting here 1 plus n minus 1 divided by 2. And when solving this, we get this is 2 plus n minus 1, that is n plus 1 divided by 2. So let's write this. So this is your lower Riemann sum. Let's calculate. So this is your lower Riemann sum. So let's calculate the lower Riemann integral now. That is equal to limit mu p tends to 0 on LPF, where this mu p is pi divided by 4n, and when it is tending to 0, n is tending to infinity. So this is equal to limit n tends to infinity, and writing this LPF. Now because I know that limit n tends to infinity, sine of nx divided by nx is equal to 1. If this angle is equal to this denominator, we are having this limit to be equal to 1. So let's work on this. I'm having here angle pi divided by 8n, so I need to multiply and divide by pi divided by 8n. But I'm adjusting this. So just multiplying and divide by 2, I'm getting 2 pi by 8n, which can be further written as, here there is 2 and we can write here in the denominator pi divided by 8n. Is it okay, fine? Okay, now let's apply the limit on this. Taking this 2 outside of this limit, and now let's take n common from this bracket and also taking n common from this bracket. So this is equal to twice. Okay, n is cancelled out with this n is cancelled out with this n. And now applying the limit, we get sine of pi divided by 8, because n tending to infinity, we get 1 by n to be equal to 0, into sine of pi divided by 8. and in the denominator, and when applying limit on this, we get this to be equal to 1. So this is twice of sine square pi by 8, and because 1 minus cos of x is equal to 2 sine square x by 2, for x equal to pi by 4 in this case. So this is further can be written as 1 minus cos of x, that is pi by 4, and cos of pi by 4 is 1 by root 2. So the lower Riemann integral is 1 minus 1 by root 2. And now finding the upper Riemann sum, that is summation I going from 1 to n, capital Mi xi minus 1. So this is summation I going from 1 to n. What is capital Mi? It is cos of I minus 1 pi by 4n. And xi is I pi by 4n minus xi minus 1 is I minus 1 pi divided by 4n. And when solving this, we get pi divided by 4n. Applying the summation on this, we get, taking this pi by 4n outside of the summation. So this is cos of 0 plus cos of pi by 4n plus cos of 2 pi by 4n up to so on, cos of n minus 1 pi by 4n. Now for this series, if I take this angle to be alpha and this angle to be alpha plus beta, then we are getting alpha to be 0 and beta to be equal to pi by 4n, right? So we have taken cos 0 as the first term for this series, right? Where alpha is 0 and beta is pi by 4n. So what is the formula for this series? It is cos of alpha plus the number of terms here are n, because we have started the series from cos 0, right? So this is n beta divided by 2 into sine of n beta divided by 2, and in the denominator we have sine of beta divided by 2. Now applying this formula further, we get UPF is equal to, I'm already having pi by 4n outside the series. So this is pi divided by 4n. Now applying the formula, we have cos of 0 plus, and what is beta? Pi by 4n. And also 2 is multiplied with this. So this becomes, n is cancelled out with this becomes pi divided by 8. And also plus 0, so this is pi divided by 8 into sine of n. Beta is pi divided by 4n and also 2 over there. So multiplying this 2, we get 8n. So here also n cancelled out with this and we get sine of pi by 8. And in the denominator, sine of beta by 2, that is sine of pi divided by 8n. So this is the upper Riemann sum for this. So let's calculate the upper Riemann integral now. That is equal to limit mu p tending to 0 on upper Riemann sum, where this mu p is equal to pi by 4n. And if mu p is tending to 0, n is tending to infinity. So this is equal to limit n tends to infinity. For mu p tending to 0, I am writing n tends to infinity and the upper Riemann sum. So now applying the limit, we are adjusting this. So here 2 remains and I am writing this in the denominator because we know that limit on this will be equal to 1. So this is equal to twice of cos of pi by 8 into sine of pi by 8. And when applying the limit, we get 1 divided by here. This limit is 1. So here we are having twice the same angles with sine and cosine with their product. And we know that 2 sine of a cos of a is equal to sine of 2a. Right? So this becomes sine of twice a, where this a is pi by 8. So this is equal to sine of twice of a, that is twice of pi by 8. That is equal to sine of, this cancelled out with this and we get pi divided by 4, which is equal to 1 divided by root 2. So the upper Riemann integral is equal to 1 divided by root 2, marking this as 2. So from 1 and 2 we get that the lower Riemann integral, which we have found to be 1 minus 1 by root 2, and the upper Riemann integral equal to 1 divided by root 2 and these two are not equal, the given function is not Riemann integral even though it is bounded, right? Okay, thank you. Stay blessed.